Alright. Hello, everybody. This is Putter, and this is our all-in-one putting system. So I'm with Group 16 today, and my name is Dylan Reuter, and I was one of the computer engineers.
I'm Ryan Pham. I'm the other computer engineer.
I'm Austin Collins, and I am also a computer engineer.
And I'm Dominic DiCaterino, the electrical engineer.
Alright, so to introduce Putter, pretty quick, Putter stands for Putting Utility and Training Resource. It's just basically a new way to improve your skills at home. Um, And yeah, just has the variation of a real golf course with some technological benefits like projection, and that's basically the introduction. We'll get more into it soon. So to get into the motivation of this project, we mainly wanted to be more cost efficient than other devices. A lot of the other devices in this field are either really big or they're super expensive, usually both. So we wanted to have something that was way more cost efficient, wanted to have all the technological benefits of the other devices, and then we also wanted to have more mobility than the other devices because a lot of them are just very big and unwieldy, and it's not something you would ever have in your own home. So this we wanted to be very consumer friendly, is what we're saying.
Some of the key objectives of the project were to keep the device accessible while also being low cost, as a lot of these things have a tendency to have a very steep price. So one of the key things was to keep it under a $500 uh, limit to really stand out, as well as our main competitors being driving ranges, as they're like, besides like putt putt courses, they're really the only other places to go. Um, with our the main objectives of the project being to have a variable grass surface that allows for a different experience with different settings, as well as being able to track the position of the ball while it's on the putter and then use that to project a potential path for the ball to be hit towards the hole, while also having two modes, practice and play, and very key to be able to support human weight, as you need to be able to stand on it to hit the ball. And with the final objective being able to interface with a mobile application via Bluetooth.
Some of our specifications for putter included a surface area of 4 by 8 feet. Next, we wanted our cost, like we mentioned, to be around $450. Our weight goal initially was only 100 pounds, but as the build went on, we had to move this specification to around 200 to 250 pounds. The surface had a 4 by 6 variable playing area with a detachable 4 by 2 standing area. This was due to the size needed to transport putter, so the detachable area allowed us to fit it into a vehicle. Next, our projection, like we mentioned, is covering the 4 by 6 play area, and this is connected to a Raspberry Pi. Uh, our sensor for this is a camera overhead that will track the golf ball on that 4 by 6 play area. And for this, one of our specs was we wanted an allowable error of no more than 1 inch for the coordinates of the image detection. Next, the computing was done by a Raspberry Pi for the imaging and projection portion, and MSP430 was used for the Bluetooth and control portion. The controls, like we just mentioned, were physical buttons as well as a phone application. And lastly, our power came from a 12 volt AC to DC power supply with a 3.3 volt DC converter for our MSP430.
For our constraints, we had a few constraints. One of is the space constraint. We want to have a 6 by 4 feet space. This because we want a small form factor to fit in small spaces and for people to have it in their house. For weight constraint, it had to be less than 200 pounds. This means that it can be lightweight for easier transport. We also had a time constraint, which is 2 months. Usually it's 3 months for a regular semester, but in our case, it was a summer semester, so it's 2 months. For economic constraints, we had to be under $450. And for our lighting constraints, in order to display the projector onto the field on the grass surface, it had to be dark. That means that we weren't able to project in a low lighting, or not low lighting actually. The cameras, we could have a night vision camera, but further on we decided to forego that, because we were able to project and see with a regular camera and project with a mildly low light.
For our block diagram, you can see our division of labor. The red and green portions were done by Dominic. The blue portion was done by Austin. The orange portion of our microcontroller was done by Austin and Dylan. And then our yellow portions of our sensors and projectors was done by Ryan and Dylan. And now we'll talk about the base and the electrical hardware. So to create a variable playing area, we needed an array of linear actuators underneath an artificial grass surface. We needed a strong wooden frame to elevate the surface and give the actuators room to be mounted. On top of this frame is where the artificial turf was secured with a layer of foam and enough slack to stretch the turf around and over the overhanged edges of the top plywood, and this grass was then stapled into the plywood. In the image on the left, you can see the very first structures of our frame. And in the middle, you can see the next step, where we added some cross beams for support, both vertically and horizontally. You can see in each corner we added some more supports to prevent any bending, warping, or breaking that might happen if you're standing or jumping on top of the surface. And on the cross beams, you can see we mounted our actuators on the tops and the bottoms, giving us a very strong, stable, and level surface to start off with. And on top of this, on the right, it is flipped upside down, but you can see the top layer of plywood with the actuators mounted to it. So on the tips of each actuator, you can see the wood block in the metal bracket, which is connecting the actuator to the oval shape you see on the top plywood piece. So this oval shape was then cut out, which allows the actuators to extend up and down and push that area of the surface up and down. And on the left, you can see some of the side paneling we added to this frame to give it a clean look. You can see the grass attached to that overhang with that thick layer of foam, with no screws in sight on the left. And then in the middle, you can see some of our screws of where we mounted the frame to. In the middle picture with the screw holes visible, this is where the standing platform was added. We decided to add an extra standing platform so that we could have a larger playing area. Since our vehicle limited how big our area was going to be, we added an extendable platform to stand on. And on the right, you can see Dylan standing and playing on top of this area. And next, our actuators. Each one was a 12-volt linear actuator. Each one of these was capable of moving up to 225 pounds. At full load, which was the 225 pounds, each actuator would draw around 3 amps at absolute maximum, and with a total of 4 giving us an absolute max of 12 amp current draw. In our testing with no load, each actuator only drew about half an amp, so we did not ever reach the full 12 amp draw from our power supply. To prevent any overheating, these actuators were rated with a duty cycle of 25%. And to achieve this duty cycle, we created a 555 timer-based PWM motor driving circuit. This was done with a 555 timer with a output transistor and a flyback diode to prevent any damage from the motors onto our IC. And you can see our schematic in the middle picture at the bottom. And then at the bottom right, you can see one of the actuators extended with the oval plate on top. And this was our first PCB, the 555 timing circuit. On the left, you can see the design, and on the right, you can see our implementation and final product. Now for controlling the actuators, we wanted physical buttons as well as Bluetooth inputs, and this was done with a MSP430 microcontroller and an HC05 Bluetooth module. This was connected to a pair of relays for each actuator, so we had a total of 8 relays. So for one actuator, you needed 2 relays, one to go up and one to go down. And in the image on the bottom, you can see that the MSP430 would input a signal to either input 1 or 2, which would switch on either relay 1 or 2. And COM1 of relay 1 was connected to the negative terminal of our actuator, and COM2 of relay 2 was connected to the positive terminal of the actuator. And so if a signal was input to input 1, relay 1 would switch and connect our negative terminal to our voltage output of the 555 timer, making the actuator move downwards as a positive voltage was applied to the negative terminal. And vice versa, if a signal was applied to input 2, the positive terminal actuator would be connected to the positive voltage of our 555 timer, making the actuator go up. And for the MSP430, this was our second PCB board. We have a 12 volt 40 amp switch mode power supply capable of providing up to 480 watts of power. This has 3 channels, and one of these was used to step down the 12 volts to a 3.3 volt level for our MSP430. This uses the LM1117 adjustable low dropout linear regulator. This is a voltage regulator that we used to power our MSP430, and you can see our PCB designed at the bottom.
For our PCB vendor, we used to find a good PCB vendor is a priority for us to ensure the success of PUTR. The vendor must have a reliable reputation while maintaining an affordable price. Quality is the utmost importance for us, and it will have to be functionally sound. When we factored all these standards, we found that JLC PCB was the perfect PCB vendor for us. They have the perfect balance of quality while keeping a competitive low price. JLC PCB also has a minimum order quantity of 5, so that allowed us to have room for error in case that a few PCBs were failed or had any manufacturing defects, or if we had any user error during that. We decided to go with a 2-layer green PCB order with yielded the fastest delivery time. If we tried a different color PCB such as red or yellow, that would considerably extend the time for delivery for us. In order for us to lower the cost, and because our design was didn't have to be small, we used a through-hole component design, and then we ordered that PCB according to that, because we were able to manually solder the components onto the board itself. The shipping time was around 1.5 weeks, and the production time was actually 3 days. Pretty fast.
All right. So this is our embedded system selection, and I'm basically just gonna go over why we decided to choose the Raspberry Pi over other embedded systems. So here's our pros of the Raspberry Pi. The first is that it was great to use with computer vision. I had previous experience using a Raspberry Pi with computer vision applications. So this made it a really strong contender because I knew that it wasn't going to be very difficult to set this up and to get it running fast for us. It's also loaded with Python, and this is great because Python is super useful with computer vision. It was free because I already had one, which is also like a very good contender just for keeping our budget straight. And then it also had plenty of USB ports for our camera and an HDMI port for our projector. And this was important to us just to make sure everything was good for our project. So some cons of the Raspberry Pi 3 was that it was lacking a lot of performance. Um, and I was looking at other embedded systems that might be able to perform better. And I saw the Jetson looks like it was pretty strong and probably could have had a higher frames per second on the camera while running the object detection. So that was a con of the Raspberry Pi. Was performance was lacking, and also it was overheating a lot. Like it was getting very hot, and I think that's partly because we were outside in the Florida summer heat in a garage, like working on this. And I think that overheating like definitely impacted the performance a lot. So that was another con of it. Moving on.
For camera selection, during the course of the project, we had to upgrade our camera to a camera with better quality to suit our needs. Initially, we had this basic USB camera that was compatible with the Raspberry Pi. However, it had a terrible fisheye lens that distorted all our points, which really made it hard for us to track and store the coordinates. It was unstable and it overheated, which yielded us low frame rates. However, plus to that, it offered us infrared night vision. And with a projector, it's pretty nice to have something to project when there's no light. And what we upgraded to was this USB webcam. It had a better quality, very square lens, and this meant that we can easily track everything without any distortion. It's also more stable. It was less wide, so more of the greens were in view, and none of the view outside of the green um, had an impact in our object detection. It also ran cooler and yielded us higher frame rates. For training the camera, before we were even able to start with the object detection, the golf ball had to be trained on a neural network. To accomplish this, we use the COCO, which is the Common Objects in Context dataset. This dataset contains a significant number of data on various items such as cars and sports balls. Using this dataset combined with other um, 100 photos and plus with our golf ball on the grass surface in different lighting, it net us an average of a confidence level of 70%. The confidence level score was the score that was displayed, and it showed how confident the object detection believed that it detected the golf ball. Once the object detection believes that it found a golf ball, it will display the square around the golf ball with a confidence level. You can see that on the image on the bottom right. You can see the golf ball is encompassed by the square, red square. It knows that it's a sports ball and that it's 97% confident that it's a sports ball. And notice that it doesn't detect that the hole is a sports ball. And that's the beauty of training. Um, but for our situation, even though we can get a lower confidence level, it doesn't matter because putter will only need its location of the golf ball, so it can display the correct path for the golf ball to travel. Um, we did have some performance issues with the frames per second. However, it didn't really impact the quality of our object detection and projection. We did use transfer learning with TensorFlow Lite. TensorFlow Lite is made for deploying machine learning models onto edge devices like Raspberry Pis. And transfer learning is a research problem in machine learning that focuses on storing knowledge gained while solving one problem and applying it to a different but related problem. And that different and related problem is PUTR, that we can uh, display and project the direction of where the golf ball can travel. And that's it for the training camera.
All right. So moving on to the projector selection. Our main goal with the projector was just having a very lightweight projector. The main reason we wanted it to be lightweight is because we knew we were going to have to put it at either a high angle, or what we ended up doing was putting it right above the golf greens. So that way it was able to cover the whole area, and also it looked the best when it was like that. So we definitely need something lightweight, something that wasn't going to be heavy if we're going to put it up high. We also wanted it to be compatible with the Raspberry Pi. This projector was, so that was another plus for us. So yeah, we covered almost all the greens. It was very lightweight. It was also super cheap compared to other projectors, which was awesome for us. Again, keeping in mind our budget. And it also had like a pretty good quality projection. It looked a lot better when it was dark, but even in like what is it, room lighting, it really doesn't look that bad at all. It also came with a remote, which was helpful when it was high up.
For Python and starting program flow, Python was our main language for object detection and projection. We used the OpenCV library for computer vision applications, and we used the graphics libraries projection such as Turtle. And Turtle helped us show where the ball should be hit, and we created a loop that will continue to update where the ball should be hit, wherever the ball landed. For step one of our starting program flow, we used object detection to find the golf ball location. And then for the step two, we used coordinates to calculate distance from golf balls to holes using our distance formula. And next, we used the drawing specified distance using the Python graphics library. And then we saved the image to project onto the surface. And then we waited for a change in the golf ball coordinates, and then looped it and updated our golf projection.
Okay, so just to get a little more in depth with the line projection, so our main objective was just getting a reasonably accurate line going from a golf ball to the hole. So the main steps that we had to take were this. So basically, we had to scale the camera coordinates to the coordinates that were going to be used by our graphics library, which is Turtle. Basically, the camera coordinates were like kind of weird and almost random. They were just like very big numbers. But we noticed that obviously, like if you move the golf ball up or down, then the x and y coordinates would change like accordingly. So we figured that all we had to do um, was put the golf ball in the middle of the greens, and from there we found kind of like our origin point, and we were able to scale it around this origin point. And then so we started treating it like our golfing greens. We started to treat that as a coordinate plane. Um, and so basically what this means was that we had our origin, and then we had different quadrants for our coordinate plane. So we had like our positive coordinate, where like the x and y coordinates would be positive, and then we had like a positive negative coordinate, where our our x coordinate was positive, but our y coordinate was negative, and yeah, so on, just like a coordinate plane you would have in school. And so that worked really well for us. We had to add some small adjustments for each of the quadrants so that the line would project accurately, but this worked well enough, and it came out really nice. As long as the camera and projector were completely stable, this would hold up very nicely. And yeah, that was basically it for that.
For the software communication side, we, as said before, use the MSP 430. Very easy and intuitive to use board. We communicated with the application with the Bluetooth network stack, as it's usable with iOS and Android, and created several APIs: the adapter, device, socket, and class. And yeah, as said before, the purpose of this was to allow the application to communicate with the actuators via the MSP430. Go ahead. Uh, for the mobile application, we used Android Studio as the IDE, as it's very intuitive to use and has a, great selection of phone emulators uh, that helps us see how the UI looks as it's developed. And the framework chosen in in hand with it was Flutter, a open source development kit that was created by Google that allows for developing applications on both iOS and Androids. The main screen for the mobile application was changed to be a more minimalist and streamlined design, as the before the preset buttons made it more clunky and overall were unnecessary, so they were removed, allowing for just a singular button for the user to connect to the putter. The Bluetooth selection screen is next, that's where the button takes you, and allows the user to select the putter device and stores the address of the putter to be used in the create a course page, as the create a course page is very integral and is very important overall with communication. And there is a feed on the in the app bar to show whether or not there is a connection with the putter, and there are 4 text fields to allow the user to customize the actuator as needed, with then the set button sends the data to the putter. Some of the major challenges we encountered through the development of the project was uh, figuring out how to transport and store it. As ideally, when we were developing it, we wanted it to be very large, but it's just not feasible with transportation and size. So we made it a little smaller and then had to separate the stand in order to transport it to continue development. And another a challenge we encountered was the mounting of the actuators to the framing was extremely difficult, and the oval tops were not as steady and easily mountable as we had hoped at the beginning. And another major challenge we encountered featured the camera and projector, as the placement was extremely important, and any adjustment would throw off any of the programming and coding that had been done before. So they needed to be as stable and unmoving as possible.
All right, everyone. Thank you for your time. I hope you enjoy our demo.